What's going on, everyone? Johnny Bannon here, the networking guru, and this is going to be our first video of our full and free CYSA course. So make sure you like, subscribe, hit that bell for notifications, share with your friends, and let's go ahead and get started on this CompTIA CySA CYSA Plus full and free course. So I'm going to move my head out of the way, and let's go ahead and jump right into it. So, for the CompTIA CYSA CySA Plus course, we're going to start at Domain 1. So Domain 1, let's go back to the title actually, is going to go over the importance of system and network architecture concepts in security operations. So in this video, we're going to touch on operating system concepts. Essentially, as a security analyst, cybersecurity professional, what do we need to protect from our operating systems? This includes Windows and Linux. More on the Windows part because in an enterprise, Windows dominates still. Things like registry keys and how to harden that system. Then we're going to go over log ingestion, and with that, what we can do with log ingestion, what kind of technologies we want to use with log ingestion, like a SIEM or SIEM system, how timing is important with that. Then also infrastructure concepts. We're going to go over serverless architecture, microservices essentially, containerization, and virtualization. Just the foundations of it, keeping in line with the exam objectives. Not going to show you how to build a container, but what you need to know about it to protect the containers in your environments. Things like how to get a good image from a reputable source, things like that, okay? How not to clone a compromised container. So let's go into it. So we're going to go over the OS concepts, log ingestion, and infrastructure concepts in this video, Domain 1.1.1. Okay. So the first thing we're going to talk about is, again, OS concepts. So operating systems are fundamental to the function of any computing device. I mean, whether we're talking a router or a server or a desktop or even a phone, we have an operating system. And that operating system is always going to be one of the biggest threat vectors for attackers. So if we have a hacker that can get root access to an operating system, they're golden, right? They're good to go. If they're an advanced persistent threat, sayonara, they're going to be living on that network for at least a year. So as security operations professionals, we must understand those OS level concepts. So we can come up with techniques and mitigation and detection steps. We know what technology we want to use and what we should use, things like EDR, XDR, DLP, but also what to look for. And we have to have that fundamental concepts. We can't be a cybersecurity professional and not know what a registry key is in Windows, right? That just, nowadays people think that's the case, but it's not the case. We need to understand the fundamentals of these operating systems so we know how to protect them. So Windows registry. So the Windows registry is something that's a big threat vector in a Windows operating system. It's the hierarchical database of Microsoft that stores configuration settings for the OS, applications, hardware, current configuration, the current user. We're going to have registry keys in there that set the configuration parameters. So the registry is divided into keys and subkeys. It's key value pairs essentially. You have the key and you have the value to that key. That can be an integer, binary value. So for example, one of the main registry keys is the H key local machine that stores settings related to the system hardware and software. So we're going to have keys, subkeys that are going to hold values that if those values could be exploited or changed, could cause issues on operating system. If something malicious creates a registry key, that can also create persistence on our system. We don't want that. We don't want them to have persistence in a backdoor or a way to always get in. So the role in security operations. So attackers often modify the registry to achieve persistence and configure programs to run on startup. Monitoring and analysis. So to defend that, we need monitoring tools. So we have things like EDR, XDR. We have something like FIM that can monitor file changes, which sometimes, in the registry, maybe it's a file that gets changed. Sometimes we have that .dat files that are in the registry. Or we can have something that monitors the baseline of our system and could alert us when there's malicious activity or possible misconfiguration. Okay, root keys and registry values. There are 5 main root keys in the Windows registry, 5 main ones with their subkeys. So we have the H key class's root, HKCR, which contains file extension associations and OLE object class registration. We have HKCU, that's the current user key. Store settings specific to the currently logged in user. That's the currently logged in user. So yes, if you didn't sign out and there can be multiple users logged in, see where I'm going here, right? That could potentially be an exploit. HKey local machine, HKLM, contains computer-wide settings and configurations. HKU stores user profile settings for all users on the computer, so not just the currently logged in user. Then we have the HKeyCC, the current config. So that's going to contain hardware and software configuration information. So for the current configuration of that device. So registry values store data used by Windows and applications. Common value types include strings, which is characters, integers, and binary data. You can even have hex data on there as well. So these values can be used to configure system settings, application preferences, and also affect drivers, which we know drivers are another big, say big thing. Everything's big in cybersecurity. You want to protect it all. But again, changing a driver could affect the whole system. Let's go ahead and jump. I'm recording on a MacBook. Let's go ahead and jump into a Windows computer I have on TeamViewer. And let's take a look at our registry editor here. This computer I have online, the internet, we're in a storm right now in Fayetteville, North Carolina, where I live, and the internet's really slow. So it's going to be a little laggy. It happens sometimes. This computer's on like a 5G hotspot. Anyways, long story short, all my other computers are traveling right now because we do in-person training, and the instructors have them offline. But here's the keys. So we can look at the local machine. We can come to hardware. We can look at UEFI. And then here's the sub key all the way down in this nested area here. And we can change these values. So if we right click, modify, or if we can even double click, again, it's really slow, but we can modify that binary data. And now you see here, we can change it from hex, we can put it into decimal. I'm going to hit cancel there. But that's where these keys live, in the registry editor of our Windows device. Let's head back to the slides. Okay, system hardening. So now that we learned about the registry keys and how they could be affected, it could be bad news for us, and we have to monitor them and just be aware of how they affect the system at a root level and how they could help an attacker gain persistence. Now let's go over something just more general system hardening of our operating system. So system hardening refers to the process of securing an operating system by reducing its attack surface. So what do we mean by that? If we open up every single service, every single port, we are just inviting attackers. If we have things open that are not supposed to, or that we don't need open, that increases the attack surface for an attacker to possibly exploit our device or devices. Now, this is true for anything, for a router, switch, firewall, server, computer. We want to reduce attack surface as much as we can while not reducing the availability to the user. So you don't want to harden the system down to the point where it's unusable, but unnecessary services that don't affect the day-to-day, disable them. We need strong password policies. Now, this kind of gets into like IoT devices, where if you're putting an IoT device or something that's COTS, commercial off the shelf, into the enterprise, where I could come in, see, oh, you got that IoT device? Let me research what's the default admin password for it. It's probably on the vendor's website. That could be bad news if you don't change that. So we want to enable strong password policies. On Windows, speaking of identity access management, we want to disable the local admin, especially for a domain joined computer. Maybe we want to have Microsoft Intune online to do some MDM monitoring, right? And you say, why is that part of system hardening? Well, it's part of the whole ecosystem of it, right? Making sure that permissions are set correctly, especially on anything local to that machine. We want to make sure that we have some sort of patching system in place. Now, obviously on a big enterprise, day-to-day sales, profitability, marketing can't be affected if we apply patches right away that could affect third-party apps. But we want to be proactive in the fact at least have a patching system. So Patch Tuesday comes around, patch a computer in a sandbox, nothing's affected, apply that patch immediately. Depending on the CVE levels as well, the CVSS scores and levels, if it's a 10 on the CVSS 3 version or baseline, so score of 10, maybe patching is very important, right? Restrict permissions. So we always want to do the principle of least privilege on our operating system and enterprise-wide, but really everywhere. So have the principle of least privilege. Only give permissions as needed for someone to do their role, to do their job. Principle of least privilege. So the impact on security. Hardening prevents attackers from exploiting misconfigured or vulnerable systems, reducing the likelihood of compromise. A basic example you'll see in every cybersecurity class is, hey, if we don't need Telnet open, disable it. Other vulnerable things like SMB, make sure it's on a updated version. Disable it if we don't need it. If we have a server that needs SMB for file share, don't point that towards the internet. Keep it internal. File structures. So let's go over the file structures of an OS. So understanding the file structure of an operating system is critical for identifying where critical system files, logs, and configurations are stored. If you're doing log dives as a cybersecurity professional, you're in a Linux machine and you don't know what's under var/log, you may be losing the job. Configurations are stored. If we have to make configuration changes in a Linux system like DHCP, DNS settings, we need to know where that's at. If it's in the etc directory or wherever, right? In a Windows machine, we have to know that our configuration files are under System32. And if an attacker gets a hold of those, they can do some malicious changes. One that I like to show people in class all the time is changing the host file, where this is where we're going to do DNS resolution first before we reach out to any DNS server. And I can point google.com to malicious IP address, right? At the local machine. So it's important we understand where these important configuration files are. An example I have up here is the SSH server settings in a computer or in a Linux server or machine. We have to know where that file system is. Now, as security professionals, what tools do we have to protect our files, to monitor them? Something called FIM. So we have file integrity monitoring. This is technology that's going to track and verify file changes. It can detect and alert us of any unauthorized modifications. We can do this like time-based. We can say, hey, I'm on clock from 8 to 4, and I'm the server admin. And maybe if after 9 p.m., if a file's changed on my server that I didn't previously authorize, I want FIM to let me know. So I want an email, I want an SMS, I want a Slack message. That's file integrity monitoring. Another little tool in our toolkit, put it right in there, that can help us monitor these file changes if they happen. Examples. Tripwire monitors changes and alerts. OSSEC provides file integrity checks. So we could do that with integrity, right? Some hashing, whatever the case may be. And then AID, another software tool that can help us track changes on Linux systems. You can look that up if you want, see how those can be used. System processes. So system processes are instances of running programs on an OS. These can also be exploited. Monitoring and managing these processes is crucial for identifying malicious activities. One of the things we can do, even if it's like a network-based process, we can do like the netstat command and see malicious data exfiltration. We can also see if we need to kill a process, because maybe it's a daemon service, which means a startup service, we can go look at the processes. We can use the kill command on Linux, like kill-9, to kill that process. Processes are always going to have what's called a PID associated with them, a process ID. We can kill a program that's maybe unresponsive, malicious, that is protected by killing that process ID. So common threats, process injection. So attackers can inject malicious code into legitimate processes to evade detection. That's something that's very hard to detect. Unauthorized processes. There could just be processes that are unexpected or not associated. We have tools like EDR or XDR, endpoint solutions that can alert us when maybe there's a process that is not part of the normal behavior, not part of the normal baseline to that endpoint or to that operating system. We have tools like Task Manager in Windows where we can go, we could go step process by process and see what's running and see if there's anything malicious. But then in Linux, we have something called top or htop or the ps command that can inspect active processes. I'm going to pause the video. I want to bring up a Kali Linux machine and show you that real time. So here we are on a Kali Linux machine. Now, don't get wrapped around this Kali. I'm not doing any hacking. Just a Debian-based Linux distro. Let's look at our processes. So we can type in htop here. We can see my processes running. And htop is pretty cool. It makes you look like a hacker. You put this up. Your boss walks by that didn't come from a tech background, but he's your TPM. Whatever. You have this running. He or she's like, yeah, they're doing good work. So there we go. If I want to kill a process in Linux, let's say I don't want to kill these processes. Let's do this netstat command. Let's open up Firefox. Let's look at this active session. Netstat ANTP. This will show me the process ID for some of these active TCP connections. Another way to kill a process, I can do, like if it's an active TCP, do the kill command and put that process ID, and boom, Firefox is now killed. Now I'm going to exit off this virtual machine because I don't want to take up my precious memory. Let's get back to our slides. Okay. Now, where were we? Yeah, processes. I put CrowdStrike on there, not just because they stopped me from traveling over the weekend one time, which really sucked, because their EDR system changed a value in Windows machines, but they're an EDR XDR solution that actually does work pretty well that can help you with this kind of monitoring on the actual endpoint. Okay, hardware architecture. Back to A+, baby. Yes, our hardware is also important too. It's not just all this technical, I'm in the matrix ones and zeros that we have to think about as cybersecurity professionals. There's also hardware architecture that forms the foundation of all computing environments that we still have to protect. Your BIOS, your UEFI. You want to make sure that you have OEM, firmware, and hardware that hasn't been changed. You have tools that can help you. You have things like a TPM chip, secure boot processes. So there's hardware-based validation mechanisms, such as trusted platform modules. We ensure only trusted software is loaded during startup. We do that by taking hashes of the OEM software, firmware, and then comparing that to every boot. And if something changes, it won't let us boot. That's secure boot. That's, I'm blanking, UEFI, right? Whew, that's bad. I'm a trainer. I should know that like that. We have HSMs, hardware security modules, dedicated devices that securely manage cryptographic keys, ensuring data encryption and secure transactions. Maybe our hard drives, our SSDs, our NVMEs. We want full disk encryption on them. We want to put something like BitLocker on our enterprise to protect our data at rest. We also have memory security. We also have implementing memory encryption and secure management. Things like an XBit or the XN bit or ASLR, something that can protect our data in use, our data in process, which is like our RAM, our memory, CPU. Now, so that was our OS concepts. Now let's go to something else, kind of more enterprise grade. Now, protecting the operating system is a big part of your enterprise. But let's talk about monitoring at scale. Log ingestion. If you work in a SOC and you don't have a SIM or SIME system, I don't know what kind of SOC you're working in, but log ingestion and aggregation is a very big, crucial part of your day-to-day as a cybersecurity analyst in creating dashboards, indexing all that big data, and creating user behavior baselines that then we can put a large learning model or a machine learning model on that'll then tell us when something's deviating from that baseline. It alerts us. It gives us a severity score and tells us maybe we need to look into it. Maybe it quarantines it itself, that device. But log ingestion is the collecting and parsing and storing of logs generated by all of our systems or various systems that we need to be aware of. Log ingestion is very important. A SIM or SIME system, which stands for Security Information Event Management, something like Splunk can do that for your entire enterprise. So we aggregate it, we ingest it, we index off it, look for critical information, create user baselines. We set up alerts, detections off those user baselines, or we can use it for a variety of different reasons, for our patching, for tracking our patches, whatever the case may be. Log ingestion gives us that single pane of glass. I know it's a marketing word, but I like to use it. It gives us that centralized visibility. It helps in incident response to create a trail, right? When we're doing our forensics or doing our investigations, our root cause analysis. So log ingestion is very important for you to understand as that cybersecurity professional. Compliance. A lot of different frameworks, compliance, things that we have to be in compliance with, different frameworks like PCI, GDPR, HIPAA, NIST, from the government. They require logging. They require logging and for the ability for your cybersecurity professionals to look at those logs. Time synchronization. So what good is logging and looking at our trail, looking at our RCA, our root cause analysis, if we don't know what time something happened and something went down, or the timing's off, we got a call at 2, we go into the logs, and it says 1993 in there. Time synchronization is very important, not just for security, but for overall, just for an enterprise to work. If you're running Active Directory, you need timing, because Kerberos relies on that. Ticket granting ticket, timing's involved in that. We need time synchronization, not only for our security operations, just for the enterprise in general. we want to make sure our timing is accurate. We can do that with different timing synchronization protocols. We have NTP, that's typically what we're going to see in the enterprise. We have PTP, precision time protocol, that gives us down to like the, I can't remember if it's micro, nano. It's very accurate and typically used in OT environments, like manufacturing, factories, things like that. We have something called NTS, which is going to add encryption onto our timing protocols as well, because NTP comes across in UDP, port 123, it's plain text, right? So we have something called NTS that can add protection on that. So, good little definition here. The impact on security operations. Discrepancies in timestamps can delay threat detection and compliance incident investigations. So if an attacker exploits an unsynchronized system, they can mask their activities. We don't have a good time. We don't have a good trail on them, good auditing. Logging levels. So I put up syslog here. Come from a more network background, but logging levels, not just in syslog, but logging levels gives you some granularity and some severity levels that can determine how you alert, what you want to be made aware of, the on-call guy or girl. It just helps us look at what the potential impact may be at a standard way. So, and for our organization, we use syslog on our network devices, and we say, hey, anything 3 and below, so level 0, 1, 2, 3, the on-call guy is getting a Slack message, email, and call. That's what we may do in our organization. But we have other logging levels. We have critical, warning, information, verbose, debug. Obviously, critical would be like a SEV1. If we have a critical system down, we're getting called in, right? So logging levels are very important. Logging levels kind of determine your alerting. It kind of determine your detection triggers, right? On when we're going to get brought in. So why logging levels matter in security operations? Overlogging can overwhelm. So we don't want the opposite, where we're doing too much. They can overwhelm storage and obscure critical events in a sea of data. That's true. These big data lakes, right? So I won't use these buzzwords, but yeah, we have these. If we log everything and keep everything in logs for years, even little debugging informational logs, that can be pretty robust, especially when we start getting into these large enterprises. But then underlogging can lead to misdetection or subtle attack patterns that maybe we don't have the manpower to log dive into every day or at the end of the week. All right. Let's take a little breath. I try to keep my videos under 30 minutes. Let's go over infrastructure concepts. Now, cybersecurity operations. We're not, we know, at an enterprise scale, we're not building data centers. We're not creating our Kubernetes clusters and at scale, having this large scale building elasticity of these applications running containers managed by Kubernetes pods, clusters. That's not what we're doing. But we need to understand our infrastructure. We need to understand how the infrastructure works, how we deliver applications to our users, and the infrastructure behind it, so that, one, we can speak intelligently, and two, we know how to protect it and what we need to be looking out for. So virtualization that was kind of the first step in taking a piece of hardware and getting the most out of the resources in it. So virtual machines. Virtualization is taking a bare metal server, and this is at the data center, the enterprise scale. I know I just showed you a VM running Kali Linux. That's my hypervisor, VMware Fusion on my desktop, my laptop. But in the data center, right, type 1 hypervisor, we have a bare metal server, that hardware, a hypervisor on top of that, Proxmox, ESXi, but who knows, since Broadcom bought out VMware, it sucks now. Sorry. That hypervisor then controls the resources going to those individual virtual machines. So every virtual machine represents an operating system, a device that we're going to have to manage, that we're going to have to patch, that we're going to have to monitor. So we may have one server in a rack, but we may have 20 different virtual machines in there that we have to ensure there's high availability as part of our roles in security. And we got to monitor all those VMs. Depending if they're Linux or Windows, we may have to put different XDR, EDR solutions on them, put them in part of our patch rotation. We want to make sure that the sysadmins have snapshots and recovery methods. We have redundancy. So if we're in a big clustered environment, we have 4 ESXi hosts. We want to make sure that we have some sort of VM motion, snapshots in there, redundancy, right? And then we have just the actual cybersecurity risks. So what do we not want happening on our VMs? Well, one, if they're attacked, they can be attacked like any other regular operating system. But if they are, then we have other risks, like those VMs the attacker's escaping the VM, getting into the background hypervisor and attacking other VMs. We have VM escape, where an attacker exploits vulnerabilities to break out of a VM and access the host. We have hypervisor attacks, where they actually just compromise the hypervisor, and then you have total control over all the hosted VMs. A lot of times this is like, I swear I've seen this before, E6i pointed to the internet. So someone can log into your E6i if they brute force your password and then they have access to all your VMs. Just something little like that. You don't want to expose the hypervisor. Keep it contained. Put it on its own VLAN, that hypervisor VM network. Containerization. It's like the evolution of it. The evolution of virtualization is moving to containers. Now, what was the fallback of virtualization? Well, from a security perspective, it was robust. I mean, we had to worry about the VMware software being attacked, hypervisors, then those individual machines also being part of the patching, the monitoring. It was just another device we had to monitor for maybe a single application. With containerization, that's a lightweight form that just has a single Docker or containerization engine, usually Docker, that's going to have all the dependencies to run multiple applications, very lightweight, on a shared host or OS kernel that we can deploy rapidly. So not only now can we deploy applications rapidly by putting it in a container, we get a container image from a centralized repository like Docker that we can trust as cybersecurity professionals. If that container ever gets compromised, guess what? Delete it, download the new one, push the code to that. It's a lot better of a system for deploying applications and services to the enterprise, and it can scale a lot better by implementing things like Kubernetes. So security advantages. Consistent environments across development, testing, and production. That's true, because we're going to have that shared OS host kernel. And then smaller attack surface. It's just a container. It's not an operating system where we have to worry about all these different system hardenings, registry keys, things like that. Now, there are some risks. Insecure images, so an untrusted container image. If where our developers are going crazy, our DevOps team, they're getting untrusted images. That's something we have to be aware of. Kernel exploits. Since it is a shared OS kernel, if some malicious threat actor were to get a hold, SSH into one of our containers, they could exploit the kernel, and then boom, there it goes up in smoke. But it's a lot easier when some container gets exploited, delete it, deploy a new one. It gives us that scalability. And lastly, we're going to talk about serverless, microservices or serverless architecture that differs from our typical monolithic web or architectures. So serverless is a cloud computing model where the cloud provider manages the servers and developers get to focus on just developing. And then we have these microservices that work together to deploy our application at scale. So security implications, reliance on the cloud provider security practices, what I would call technical debt, learning the serverless architecture and what control you have as a security team. When it comes to anything cloud-based, you're always going to worry about IAM, Identity Access Management, and securing that application code that gets pushed to the cloud, just making sure that what you can control is protected. That usually comes down to basic hardening again of your cloud environment, good IAM, multi-factor authentication, but understanding that serverless architecture, you're not managing a server anymore that's going to host the backend in the database. You're going to have these functions as a service. You have a database, an individual database in Azure called Cosmos. You have Azure Functions. You have an API gateway. All those microservices working together. That then you have to also think about microsegmentation for those services. So a lot we have to worry about with serverless architecture. But again, we're not going to deep dive too into it. We just got to have a basic understanding as a security professional. Okay, let's go ahead and do our quiz. So we are at our learning management system now. You can also purchase this online if you want. It's our academy.trepatech.com. And let's go ahead and do our CYSA quiz. Now I'm starting this, so I only have one lesson up there, okay? So by the end of this will be full. We'll have flashcard, practice exams, and quizzes. Let's go ahead and head to the lesson here. Domain 1.1. Let's go ahead and take our domain quiz. Let me zoom in here. Question 1. Which component of the Windows registry is most commonly targeted by attackers to maintain persistence on a compromised system? So we're talking about persistence. That's like backdoor, like leaving something on that machine so we can always get back into it. That's going to be the local machine. That's the H key local machine that we have to worry about. That's when it comes to most commonly targeted by attackers to maintain persistence. So C, H key underscore local underscore machine. And there's an explanation down there. Pause the video if you'd like to read. Question 2. Which of the following is the most critical reason to ensure time synchronization across systems in a security operation? So we're going to go with C here. Enable accurate correlation of events during incident investigations. We want to have accurate timing. We want to make sure we can create that audit trail when it comes to our security operations. There's a whole bunch of different reasons why timing is important, but we're going to go with C here. And there's the explanation. Pause the video if you'd like to read. Question 3. During system hardening, which of the following actions is not considered a best practice? I mean, this one's kind of a give me. But yeah, B, enabling administrative privileges for all users. That's not what we want to do. We want less privileges, less things that if we don't need it, don't use it. Pause the video if you'd like to read the explanation. Question 4. In a containerized environment, what is the most significant security risk associated with improperly managed container images? So when we get an insecure containers, we didn't get it from a reliable source, doesn't have integrity, could be some malicious, that can infect the entire environment, all of our containers. So we're going to go with D. Introduction of malware or vulnerabilities into the environment. Pause the video if you'd like to read the explanation. Question 5. Which file structure directory is most likely to contain critical system configuration files in a Linux environment? Critical system configuration. So this is going to be something that affects the entire system or could affect our users. It's going to go with the etc. The etc folder is going to contain critical system information. In here, there's things like the shadow file, the password file that shows all the username and passwords. Other things like that, like our DNS settings, DHCP settings, and the etc directory. So we're going to go with C, etc, or etc. Pause the video if you'd like to read the explanation. Question 6, last question. Let's go for that 100. Which of the following best describes the difference between virtualization and containerization? So A is not it. Containers use kernels. Looking towards B, virtualization does not scale more effectively. And virtualization does not eliminate security risks. It has more security risks than containerization. So I'm going to go with B. Virtualization uses virtual machines with separate operating systems. That's true. Hypervisor can have a Linux, OpenBSD, technically a Mac, and a Windows operating system all on one hypervisor. While containerization isolates applications in lightweight environments. Let's go that big 100. Pause the video if you'd like to read the explanation. And let's go, guys. We did it 100%. So I want to thank everyone for viewing. Stay tuned for our next video. We're going to finish up domain 1.1. And make sure you like, subscribe, share it with your friends. If you're interested in virtual training or our full course, click the link in the description below. I'll see you in the next video.